So when we last left off, we were discussing reduction of ketone functionalities, and we discussed how reduction can be thought of as addition of a hydride equivalent or a hydride nucleophile into our carbonyl functionality. So another method of generating alcohols from carbonyl compounds is via addition of a Grignard reagent. So alkyl, aryl, and vinylic halides react with magnesium and ether or THF to generate Grignard reagents. So in turn, this Grignard reagent, which is written as RMGX, is an organometallic compound. There's an alkyl metal bond present. So we can take any alkyl, aryl, or vinyl halide, and upon treatment with magnesium, we can generate the corresponding organometallic Grignard reagent. For those who are curious about the mechanism for formation of a Grignard reagent, it's a quite interesting mechanism as it's a radical non-chain mechanism. So in the first step, magnesium serves as a reductant. And then in the second step, we end up with combination. And that in turn gives us our desired carbon-magnesium bond. A Grignard reagent can be thought of practically as reacting very similar to a carbon-centered anion. So for example, if you take a Grignard reagent, the Grignard reagent will react as a nucleophile and add 1,2 into ketone and other carbonyl functionalities. So this provides us a useful method of generating substituted alcohols from the corresponding ketone. So Grignards are strong nucleophiles because they're quite highly polarized. You can think of a Grignard as reacting similar to a carbon-centered anion. Does this idea make sense so far? So we can generate Grignard reagents from any alkyl, aryl, or vinyl halide, and they serve as relatively reactive carbon-centered nucleophiles. Are there any questions so far? Any questions so far? Okay, so the nice thing about Grignard reagents is they react with the carbonyl of most functional groups. They add in a 1,2 addition pattern, and this generates an intermediate alkoxide, just like from our reduction with hydride equivalents, we make this intermediate alkoxide and we protonate it with acid during the quench step. There are some cases where this intermediate alkoxide can be utilized and can be trapped with a variety of electrophiles. So there's a lot of creative things you can do by chaining these reactions together. Okay, so in terms of the mechanism, Grignard reagents act as a nucleophilic carbon-centered anion or a carbanion. The Grignard reagents will add to the carbonyl group in a nucleophilic 1,2 addition, and the intermediate alkoxide is then protonated to produce the alcohol. So we have 1,2 addition, and then we have a protonation step, and we can draw that out. There we go. And that generates our corresponding alcohol. Any questions on the mechanism for Grignard addition? Well, an example of this, just like in the laboratory that we're going to be working on, you can have 1-methyl-butyl magnesium bromide, which reacts very similarly to the following carbon-centered anion. So the Grignard is an organometallic reagent that reacts very similar to a carbanion in terms of both its strength as a nucleophile and in terms of its basicity. Another example, if we want to do an aryl halide Grignard derivative, would be phenyl magnesium bromide, which functions equivalent to an sp2 carbon-centered anion. Does that answer your question? Perfect. So in terms of Grignards and acid-base chemistry, there's a main constraint when you're dealing with Grignards is that Grignards are basic reagents and they can react with alcohols, amines, carboxylic acids, and other acidic and protic functional groups, generally with a pKa of less than 20. That's a good benchmark. Acid-base reactions can compete with nucleophilic addition reactions, and Grignard reagents must be protected from atmospheric moisture to prevent protonation. So water is certainly acidic enough to react and protonate a Grignard reagent. So in the event that you do protonate your Grignard, it converts the Grignard into the alkane via protonation. So if you have a carboxylic acid, which has a pKa of around 4.7, the Grignard, rather than engaging in nucleophilic addition, will engage in the much faster, kinetically, it will engage in the much faster protonation step. And that in turn gives us our corresponding alkane. Does everyone see how acidic functionalities can protonate the Grignard reagent and thus quench the Grignard reagent, preventing the desired 1,2 addition from occurring? Okay, perfect. So for example, if you try to run the following reaction, would you expect this reaction to proceed as drawn? If you have one equivalent of Grignard, would you expect this reaction to proceed as drawn? We have a ketone, we have our Grignard. It looks good, right? What does the class think? Will this reaction proceed to completion? No, exactly. We have an alcohol. And so rather than engaging in the desired 1,2 addition, the Grignard reagent will instead engage in an acid-base reaction with our protic alcohol, and we would instead just generate the anion, which when quenched would just regenerate our reactant. So our Grignard would not be able to undergo 1,2 addition because it is quenched by a rapid acid-base reaction. Does that idea make sense to everyone? So you have to be on the lookout. If you have an acidic functional group, that acidic functional group will in turn react with your Grignard reagent and consume your Grignard reagent. Does that make sense? Any questions on Grignard reagents and incompatible acidic functional groups? Okay, so let's keep going then. And let's talk about the reaction of Grignard reagents with different carbonyl compounds. So generally aldehydes are more reactive. So formaldehyde is a highly reactive aldehyde equivalent and will readily react with Grignard reagents via 1,2 addition. And so formaldehyde is a useful method of installing the following methylene motif containing an alcohol. So it's a nice way of adding one carbon to your base structure. By the same token, you can install a range of other functional groups via reaction of your Grignard reagent with aldehydes and ketones. So you can install a phenyl group using the phenyl magnesium bromide Grignard reagent. If you want to generate a tertiary alcohol, a wonderful way of doing that is via addition of a Grignard into a ketone. All of these mechanisms follow the general mechanism of 1,2 addition of our Grignard reagent into the carbonyl functionality. Any questions on this example? Any questions on this example? Okay, let's keep going then. And let's talk about what happens when we have esters. So esters can yield tertiary alcohols upon reaction in which 2 of the carbon substituents come from the Grignard reagent. So the key thing to note is we need 2 equivalents of our Grignard reagent. In this case, we observe subsequent 1,2 addition of 2 equivalents of Grignard reagent to yield a tertiary alcohol with 2 of our Grignard alkyl chains installed. Thus, you need at least 2 equivalents of Grignard reagent for complete reaction. 1 equivalent of Grignard, if you're reacting 1 equivalent of Grignard reagent with your ester, you'll see a mixture of the alcohol and ketone product. In terms of carboxylic acids, Grignard reagents do not add directly to carboxylic acids. They undergo an acid-base reaction, generating the hydrocarbon for your Grignard reagent. So the carboxylic acid functionality is substantially acidic. And as a result, the basic Grignard reagent will react and engage in an acid-base reaction rather than 1,2 addition. Does this idea make sense to everyone? Does this idea make sense? Okay, so let's just showcase for a moment the mechanism for how esters will react with Grignard reagents. So suppose we have a generic ester and we are treating it with, let's do isopropyl magnesium bromide, and we're treating it with 2 equivalents. So as part of our first step, the Grignard reagent will add in to our ester, and we will generate the following oxygen-centered anion. Now, the main difference compared to traditional compared to the traditional reaction of a ketone is that this alcohol, just like in the examples that we covered for reduction of esters, this alcohol is a reasonable leaving group. So we can collapse this tetrahedral intermediate down, and in turn, we would regenerate our carbonyl functionality. So we've gone from our ester to an alkyl ketone. From there, once we have our alkyl ketone, that alkyl ketone is going to be substantially more reactive than a typical ester. And as a result, our Grignard reagent will add into our generated alkyl ketone a second time. And this time, no matter how much we try, is there anything that we can kick out? Is there anything that we can kick out as a leaving group for this tetrahedral intermediate? Is there anything that we can eliminate for this tetrahedral intermediate? No, all we have are carbon-centered. All we would be able to kick out would be carbon-centered anions. Carbon generally is not a good leaving group, so we're not going to collapse this intermediate down. And instead, once we have this intermediate alkoxide, we'll just protonate it, and that will generate our desired dialkyl ketone. Does this example make sense to everyone? Any other questions that I can address? Okay, so let's keep going then. And in this case, we're looking at two major reactions, and we're asked to predict the product for each of these reactions. And if possible, I'd like to see students drawing the mechanism for these reactions. So let's work through these two examples, and I'd like you to share your proposed responses in the chat verbally or using the annotate tool. And I'd like to see some students draw out their proposed structures for the products for these two reactions. And we'll discuss this example in about 4 to 5 minutes. So in the first case, we have an aldehyde and our Grignard reagent. The Grignard reagent will add into our reactive aldehyde and generate the corresponding alcohol. So as drawn, as the students sharing their responses on the annotate tool, they drew the corresponding 1-to addition. We have our alkoxide anion generated, and the alkoxide anion is then protonated to give our desired alcohol. Yep, and the student proposed response for the desired product and mechanism looks reasonable for this first step. So let me clear annotations and just redraw the mechanism. So we have 1,2 addition that in turn generates the corresponding alkoxide intermediate. And then from there, our acid quench in the second step generates our desired alcohol. Any questions on this first example? Any questions on this first example? Okay, so let's work on this second example. Let's work on this second example here, and let's try to predict the products for this second example. So in this case, we have an ester, and that's why I specified that we're using an excess amount of Grignard. So we see we have addition of our first equivalent of Grignard reagent, and this tetrahedral intermediate can then collapse down and kick out our leaving group, which in this case will kick out our alcohol. So after kicking out our alcohol leaving group, we still have another equivalent of Grignard. Oh, if you could draw another equivalent rather than drawing the arrows from the same structure. But the logic is correct. The second equivalent is going to go and attack and add 1,2 into our carbonyl. Once we generate the alkoxide intermediate from the second addition of our Grignard reagent, that alkoxide intermediate is then protonated during the quench. Perfect, exactly right. So let's redraw this mechanism and let's talk through this mechanism. Oh, sorry. For the addition of Grignard reagents into esters. So we have our first equivalent of Grignard reagent that will add in, will generate this intermediate, tetrahedral intermediate. The tetrahedral intermediate will collapse and will kick out our most competent leaving group, which is our alkoxide leaving group. That in turn gives us a ketone. The resulting ketone gets attacked by a second equivalent of Grignard reagent. And then the resulting alkoxide ion that is generated is then protonated during our quench to give us the following product. It's important to think when you begin to predict products for a reaction, and it's important to be able to draw out a proper mechanism, just showing step by step, how do you get the product under these conditions? The added alkyl chain has 2 carbons. Does that make sense? Perfect. Let's do another example. So I'd like you to predict the products from this following reaction now. So we're looking at this third reaction now, and I'd like us to predict the products from this reaction. Yep, so we have a protic functional group, a carboxylic acid, and that's going to react via an acid-base reaction with the 1 equivalent of Grignard reagent that we have. So we'll just end up with no reaction. We'll just regenerate our reactant. One thing I want you to note is you should pay attention to the equivalence, because you can force these reactions to occur, but we're not going to talk about that too much in this class, as that's saved for later classes. But just pay attention to the amount of equivalence, as that determines the products that you will get out from these reactions. So what we're now going to talk about, we're now going to introduce, is the mindset for planning out a synthesis. So this is often taken from the seminal text on this topic, which is the logic of chemical synthesis, which is a really good introduction to this idea of retrosynthesis. So let's talk a little bit about what is retrosynthesis and how is it used in terms of planning out a series of reactions to make a desired product. So retrosynthesis is designing a step-by-step series of reactions and reagents to generate a product by working back step by step from the product to each intermediate reactant. So you're working backwards. So if you have your starting material and your product is B, here's your forward reactions, and retrosynthesis traces back through defined intermediates and traces back from your product to easily sourced and easily available reactants. That's the goal of retrosynthesis. We're working backwards. We use a retrosynthetic arrow to note that the product can be made from the reactant. So this arrow is a retrosynthetic arrow and essentially says A can be made from B. You then also want to note the conditions needed for this conversion. So there are a few common retrosynthetic operations that I want you to think about. And I personally like to classify the reactions that I've learned into these categories. So the first of which is a functional group conversion. So two functional groups can be interconverted using known reaction conditions. Be careful to note the stereoselectivity and specificity for each reaction. Remember, stereoselectivity, the reaction is biased to generate one stereochemical product. Specificity, if you start with one stereochemical arrangement or geometry, you'll get a defined product. Okay, so a ketone and alcohol, for example, can be interconverted through reduction or reaction with a Grignard reagent, right? So does everyone see how if we wanted to make this alcohol, we could make it via reduction of this ketone, right? If I take this ketone and I treat it with sodium borohydride and methanol, I will get out this alcohol. Does that make sense to everyone? So working backwards, we can see I can make this alcohol from this ketone. Does everyone see how the retrosynthetic arrow works backwards, and then our reaction conditions go forward? Does everyone see retrosynthesis? We're working in reverse. Forward reaction is the set conditions needed to go from our reactant to our product. So we can go from a ketone to an alcohol via reduction. Does that idea make sense? Okay, so the next major retrosynthetic operation is a bond forming or bond breaking transform. So a transform quite simply changes the structure or connectivity of atoms in the molecule. For each bond forming and bond breaking event, yes, it's saying how would you get A from B? Yeah, and the reason why we like to think backwards from product to reactant is because we may not know the exact series of steps to go from reactant to product at the onset, but if we think about it working backwards step by step, it can help reveal to us patterns or trends or strategies that we can use in our forward route. So a transform looks at changing the structure or connectivity of atoms in your molecule. For each bond forming and bond breaking event, we can separate out the product into synthons containing the desired electron density or functional groups needed for a reaction. Now, this is the really powerful part. And you may think, oh, well, our tool set's pretty limited. We only know a certain number of nucleophilic and electrophilic species right now, but we will learn more. So thinking about things in terms of synthons lets you plan out your routes more efficiently and effectively. So for example, we can make alcohols from ketones using a Grignard reagent. So if this is our target, so that this alcohol is our target, we can choose to break one of our bonds and separate it out into our synthons. Now, for this bond forming event, generally we're going to need a nucleophile and an electrophile. So we're going to designate the nucleophile as our aromatic group and our electrophile is going to be the carbon attached to this alcohol. So this is our electrophile. Now, what is a species that has the following arrangement of atoms that is electrophilic at this carbon? What's an equivalent? What's an equivalent of this carbon-centered cation? What's an equivalent of this electrophile that we know? What has the similar electronic profile? Carbonyl, exactly. So we convert our synthons into actual retrosynthetic fragments. So this is going to be our electrophile. It's electrophilic at this carbon. Okay. What about our nucleophile? What's an equivalent of this carbon-centered anion? What's an equivalent of this carbon-centered anion? Oh, that this symbol is indicating equivalency. Yeah, this is a symbol used to designate this is equivalent or functionally equivalent. So continuing on with this point, what is an equivalent for this nucleophilic carbon-centered anion that we learned about previously? Do we know something that functions like a carbon-centered anion? A Grignard, yep. So this will be our nucleophile. Now, you may say, in this example, it looks relatively constrained in terms of what you can do, but the reason why you think about things in terms of synthons and then fragments is that by going through synthons, you can start to notice connections and start to see some patterns. You can start to exercise a little more creativity in terms of what functional group am I going to use for that synthon. Now, in our forward reaction, if we wanted to make this product, we'd then just mix this ketone and this Grignard in THF, and we would generate this desired alcohol. So we've gone from our retrosynthetic, reverse, working backwards. We figured out our two fragments, and now for our forward reaction, we combine our fragments and we specify the reaction conditions. Does everyone see how it helps you dissect molecules, how it helps you start to break complicated molecules into pieces? So this is a very useful tool as it helps you more efficiently separate out and understand how to put together the fragments in your molecule. So now, just as an exercise for this, is there another way that we can disconnect and start to break this molecule apart to get other simpler fragments? Are there other retrosynthetic disconnections that we can make? Are there other bond forming transforms that we can use? Right? We broke this bond between the phenyl ring and our alcohol. Is there another bond that we can break? If we're on the idea of using Grignard reagents, would anyone like to draw on this structure another bond breaking event that we can use? And there are many possible solutions for this. So, for example, could we just as easily break this bond and disconnect this bond into fragments? Yeah, you can break it into the following fragment, synthon. And then these are equivalent to addition into a carbonyl with methyl Grignard. And there's no single right answer for this. There's no single right answer for this. But it opens up a path for creative solutions, and it opens up the path for breaking apart molecules in a logical manner. So if I wanted to make this alcohol, I would take the following ketone. I'd react it with methyl magnesium bromide in THF, and I would get my desired alcohol out cleanly. Is there another disconnection that we can utilize? Is there another disconnection that we can make? And it doesn't have to be perfect. You can try it and you can experiment. One potential guiding principle that's important to consider is that you want to partially respect the inherent sort of distribution of electron density in your product. So we know that this carbon is going to be partially positive. So then we'd ideally want to see a bond forming event with a partially negative fragment adjacent. So we've seen already that we can break two of our bonds. What's the last disconnection that we can make? What's the last disconnection that we can make? Would anyone like to try and draw it? So we've broken off the methyl group, we've broken off the phenyl group. What else? What's another way that we can make this alcohol? Yep, exactly right. We can disconnect our isopropyl fragment. That would give us this isopropyl anion fragment. The following cation fragment. And then these fragments are equivalent to isopropyl, just N-propyl, sorry about that, N-propyl, and the following methyl aryl ketone. So does everyone see how we can systematically break bonds in our target structure and simplify our target, simplify our product into fragments that are easy for us to get and easy for us to make? And from that, we can plan reactions and write out defined synthetic schemes to make any product that we want. So for example, we can take this methyl ketone, react it with propyl magnesium bromide, followed by H3O plus, and that generates our desired alcohol. So we've already come up with, in this single example, 3 different methods to prepare our desired product. Does this idea of a bond forming transform make sense? Okay, so let's look at another example. So generally we aim to reduce our product to the simplest possible accessible starting materials. In some cases, you may be asked to design a synthesis starting from a defined product. So for example, if we're asked to prepare the following, so in this case, we are asked to prepare the following product. So this is our target from the following starting material. So what bond breaking event, so working backwards, what bond breaking transform or what bond forming transform can we use retrosynthetically to go from our product to the reactant? So if I wanted to trace back to this reactant here, let's say I had this material on hand, which bond would I break to trace back to this fragment? What bond would I break retrosynthetically? Or thinking about this another way, what bond is present in the product but absent in the reactant? What bond has formed when we made our product?
The double bond.
Sorry, what double bond? So starting from our reactant, yes, our reactant has the carbon-oxygen double bond. That's correct. In our product, it's absent. What other bond is formed? What other bond is present in our product? And I noticed one of the students circled that this propyl group is present in the product. And so as a result, we can think of it in terms of that this bond, this carbon-carbon bond formed as we went from our reactant to our product. So let's break that carbon-carbon bond, and that gives us the following fragments. And we know that this carbon-centered anion can just be drawn as a Grignard reagent. So if we wanted to prepare this product from the following reactant, all we would do is we would fill in our reaction conditions based on our retrosynthesis. So we'd use our N-propyl magnesium bromide in THF as our first step, and then we'd quench with H3O+. And that would give us the desired tertiary alcohol. Does that idea make sense? Where you look, what bonds have we formed? So then we can work backwards from that and figure out what reagents would we need to form our desired bonds. Does that make sense?
Could you show the mechanism for it?
Sure. So in this case, we have our starting material, which is our ketone. The N-propyl magnesium bromide attacks the ketone. We generate the following alkoxide intermediate, and then H3O plus protonates our protonates our alkoxide intermediate, and that generates our resulting tertiary alcohol. Does that make sense? Okay, so let's try to apply what we've learned to another example. So what reagents and reactants would you use to synthesize the following molecule? So retrosynthetically, how would you make the following product? So you can have it as a one-step or multi-step process. And ideally, I'd like to see students work back from the product to the reactants and fragments. So the student broke this bond and traced it back to this ketone and Grignard fragment. So the student broke the following carbon-carbon bond and traced it back to the following ketone and Grignard reagent. That's reasonable. That's one perfectly reasonable solution. Does anyone have another proposal? So there are many correct options here. And what I want you to think about is how could we simplify this structure substantially? And I'll have some goals. These are some interesting targets to consider. One, I'd like you to start from an ester. That's one goal. And two, I'd like you to start from fragments that are 6 carbons or less. So that first response was good. And now we're going to add to it and we're going to make some additional goals. Let's say we want to make this compound from an ester and something that's 6 carbons or less. And again, I always like to label my electronic environment. And so if we have a partial positive charge, this carbon attached to this oxygen is typically going to be quite electrophilic. So then with that information in mind, we can think of our adjacent centers as nucleophilic, and we can trace this pattern all the way down and starting to look and see which bonds can we break, which bonds can we form. So does anyone have a suggestion? How would we get from an ester, or how would we get from something that's 6 carbons or less? And there's plenty of space, but what I would like to see is some use of the retrosynthetic arrows. So when you show your bond breaking, draw your fragments and then draw the forward process if possible. And there's plenty of space, so don't be shy to share your responses. There's plenty of spots on the class whiteboard for students to draw. So we have one student showing this bond breaking event, separating it into the following cyclopentyl Grignard reagent and acetone. Yep, that satisfies the 6 carbon or less requirement. And if you have trouble with the fragments, that's okay. The reason why I'm emphasizing going through the fragments is it allows you to draw, to think creatively about how can that fragment be written? How can we take that synthon and convert it into a useful reactant? Because we'll learn different equivalents for this carbon-centered electrophile, different equivalents for this carbon-centered nucleophile. And thinking in terms of fragments can help you sort of sort your thoughts out a little more readily. But this is good. This is really good. So let's talk through this first example. So we checked off our 6 carbon or less requirement. So we broke the following bond. So for this route, we trace this back to the following fragments. Which we in turn can draw as equivalent to acetone and this cyclopentyl magnesium bromide Grignard. So in our forward sense, we take acetone and treat it with this Grignard reagent in THF. That's our first step. Then H3O plus, and that would give us our desired product. Perfect. Okay, would anyone like to take a shot at figuring out a bond breaking event to get to an ester? So I'll redraw my So how can you trace this back to an ester? How can you prepare this compound from an ester starting material? So let's take about another 3 to 4 minutes and try to break out the annotate tool to draw out our proposed responses. So the student traced back this starting material to this cyclopentyl ester. Yep. And we learned previously that we can make alcohols from esters via the addition of 2 equivalents of a Grignard reagent. The THF is in the same step as the Grignard. The THF is the solvent. But otherwise, that synthetic plan looks perfectly reasonable. So let's talk through the logic behind this. So the one thing that you have to note for esters is that you must add 2 equivalents of the same Grignard reagent fragment. Since we have 2 identical carbon fragments, this opens up a unique opportunity to generate our product from an ester. So that gives us 2 CH3 minus fragments, and then the following I like to draw this as like a 2+ fragment. And the equivalent to each of these fragments would be the methyl magnesium bromide and our corresponding ester. So then in a forward sense, we'd have the following ester. And we treat it with 2 equivalents of methyl magnesium bromide. Oops, let me write this as CH3 in THF. That will be our first step. And then our second step, we'd quench with acid. And that would give us our desired tertiary alcohol. Notice, this is one part where strategy comes into play. When you have 2 of the same alkyl group adjacent to an alcohol, retrosynthetically, that is a signpost that we can go through an ester. Because esters, we have addition of 2 equivalents of the same Grignard reagent. Does that idea make sense to everyone? And does everyone see how we can tailor our synthetic strategy to go from certain starting materials? If you only have certain starting materials on hand, we can leverage that and we can design a synthesis using what we have. Any questions on these examples? Okay, let's keep going then. And I'll ask, what reagents and reactants would we use to synthesize the following molecule? And I'd like to see multiple proposed student responses for this to prepare the following compound. And generally, you want the simplest possible fragments. You want the simplest possible reactants. And just as a challenge, I'd like us again to stick to the first condition would be 6 carbons or less for each fragment. The second condition would be 5 carbons or less. And there's plenty of space in the class whiteboard. And if you have any questions, don't be shy to ask. So we cut the drawn carbon-carbon bond to break it into a cyclopentyl anion fragment and a carbon-centered electrophile. An equivalent for that cyclopentyl anion would be this cyclopentyl magnesium bromide Grignard reagent. And the equivalent for our carbon-centered electrophile would be an aldehyde. Yep. So that first proposed route meets the 5 carbon or less requirement. Yep. There's another proposed route that we can look at, but let's log that one. So we broke the following carbon-carbon bond. And that leads us to this cyclopentyl anion fragment and the following electrophilic fragment. These fragments are equivalent to cyclopentyl magnesium bromide and the following aldehyde fragment. So in practice for our forward reaction, we mix these two reagents in THF, and then we quench with acid, and that gives us our desired product. So as you can see, retrosynthesis often makes it easy to parse complicated structures into simple synthetic schemes. So does anyone have a suggestion for 6 carbons or less? And I'm surprised so far students haven't tried to utilize reactions outside of this chapter, but that's okay. As long as you meet the conditions for these retrosynthesis problems, anything is fair game. So breaking the carbon-carbon bond on the opposite side of our alcohol, So the equivalent for our carbon-centered anion is desired isopropyl magnesium bromide Grignard reagent and the corresponding aldehyde. Yep, so that other bond breaking event is a great way to generate the desired product from fragments that are 6 carbons or less. So on our second bond breaking event, I'll use a different color. We can break the other carbon-carbon bond, and that gives us the following fragments. These fragments are equivalent. And reaction of these two fragments followed by a quench with acid yields the desired alcohol product. Notice that a secondary alcohol is typically derived from an aldehyde. Does this example make sense to everyone? Okay, so let's do another example and let's talk a little bit about some strategies to handle other functional groups. So, Grignard reagents and other functional groups. Well, Grignard reagents cannot be prepared from an organohalide if there are reactive functional groups in the same molecule, such as proton donors. So alcohols, amines, thiols, carboxylic acids, no go, you'll end up with protonation. You also can't have an aldehyde, ketone, amide, nitrile, nitro, or sulfonyl group present in your molecule because your Grignard will react with it. Unless you want an intramolecular reaction to occur. So you have to make sure that if you're trying to make a Grignard that you don't have an incompatible functional group. Now, what we're next going to talk about are reactions of alcohols. And through this chapter, we're eventually going to come up with some methods for masking and minimizing undesired side reactions and masking acidic functional groups so we can make Grignards while retaining alcohol-like functionalities in our molecule. Okay, so we're going to cover some common textbook reactions of alcohols. Many of these should be familiar from Organic Chemistry 1, but we're going to talk through the mechanism and make sure we're comfortable and that we understand how these reactions work from a mechanistic perspective so we can utilize them in synthesis. So tertiary alcohols react with hydrochloric or hydrobromic acid via SN1 reaction through a carbocation intermediate. The key thing to note, your generated alkyl halide stereocenter is racemic. This reaction occurs with no stereo control. We can attack from either face of the carbocation. Any question for tertiary alcohols? So tertiary alcohols can undergo substitution via an SN1 mechanism. The SN1 mechanism inherently lacks stereo control, and you often generate a racemate. So let's look at what happens when we have a primary or secondary alcohol. So if you want to convert a primary or secondary alcohol into an alkyl halide, the primary or secondary alcohols can be converted into halides by treatment with thionyl chloride or phosphorus tribromide. Now, it's important to note that hydroxide is not a good leaving group, so it must be converted into a good leaving group via reaction. So in the case of thionyl chloride, we make the following leaving group. And as we can notice, if we look at this leaving group in detail, this is a resonance stabilized anion, and our electron dense and we have a range of electron withdrawing and electronegative groups as part of this leaving group, which in turn can help delocalize and stabilize our negative charge. So we've converted our alcohol into a much more capable leaving group via reaction with thionyl chloride, which looks something like this. By the same token, when our alcohol reacts with phosphorus tribromide, we also generate a very effective leaving group. Once we have our leaving group in place, we displace our leaving group via an SN2 mechanism. This yields our alkyl halide with inversion of stereochemistry. This is a textbook SN2 reaction, and it proceeds with inversion of stereochemistry. Does this make sense to everyone? Any questions on this? Okay then, so let's keep going. Another method to activate alcohols and convert alcohols into more effective leaving groups is via converting the alcohol into a tosylate. So a tosyl group is this para-toluene sulfonyl chloride. This is our tosyl group. So a reaction of an alcohol with p-toluene sulfonyl chloride in the presence of a base such as pyridine yields an alkyl tosylate. Alkyl tosylates are great leaving groups that react like alkyl halides. Now, the nice thing about generating the tosylate is it does not involve breaking the carbon-oxygen bond, so the configuration at your chiral center is maintained. So for example, if you start with the following alcohol and you treat it with tosyl chloride and pyridine, you will see retention of stereochemistry. By comparison, if you treat this alcohol with thionyl chloride and pyridine, you will generate the corresponding chloride with inversion. So these are two methods from an alcohol to generate a capable leaving group. Tosylate formation occurs with retention, while generation of the alkyl halide using thionyl chloride or phosphorus tribromide occurs with inversion. Does everyone see this distinction? Does everyone see how these two methods are complementary and have different purposes? Okay, so let's keep going then. So one use of tosylates is to prepare ethers. So when preparing ethers, this is a SN2 reaction of an alcohol. So when we have two main options. We can either go through the alkyl halide, which is the top route, or the tosylate, which is the bottom route. If we're preparing our ether from the alkyl halide, this process proceeds with two inversions. We have an SN2 reaction to install our halide, and then a second SN2 reaction when our halide is displaced. So we have one inversion to make the halide from the alcohol and one to substitute the halide. Thus, the product has the same stereochemistry as the starting alcohol. So we start with R octanol, we end up with ethyl R 1-methyl heptyl ether. So this is a classic example of a textbook double inversion. In contrast, the SN2 reaction of an alcohol via a tosylate proceeds with one inversion. The only inversion step we have is the SN2 displacement of our tosylate, because as we recall, formation of our tosylate occurs with retention. Thus, generating an ether using the tosylate and by displacing the tosylate, we get the opposite stereochemistry to our starting alcohol. So this is a single inversion. Does this distinction make sense to everyone? So we have two different routes, two different sets of conditions to make two different ethers with two different stereochemistries. So this allows us to control the stereochemistry of our product. If we want retention, we go through the alkyl halide because it undergoes a double inversion. If we want inversion of stereochemistry, we go through the tosylate displacement because the tosylate is installed with retention, so then the SN2 results in inversion. Does that idea make sense? Okay, perfect. So to cap off this example, let's summarize and let's predict the products of the following reaction. And I'd like you to show the products after each of these two steps. So we have a two-step reaction, 1, 2. So we have two products that I'd like you to predict. So we have an alcohol with stereochemistry, and I'd like you to predict the products from these two reaction steps. And I'd like to see some drawings of the reaction products shared on the class whiteboard. And there's plenty of space on the class whiteboard, so don't be shy to share your responses. So in the first step, we treat our alcohol with phosphorus tribromide and ether. So these are textbook conditions to make an alkyl halide. And is that alkyl halide generated with retention or inversion of stereochemistry? That's a central question we have to answer. What is the stereochemistry of our products? So as students are starting to note in the chat that treatment with phosphorus tribromide installs our alkyl halide, you don't need to draw a mechanism, but I'd just like to see the product stereochemistry and the predicted product. But the mechanism certainly helps in that, for sure. So we have a student predicting at the end of this two-step sequence, we'd install our thiophenol with net retention. Well, after the first step, treatment of our alcohol with phosphorus tribromide installs the bromide with inversion. That's exactly right. So let's talk through this example. So in the first step, our alcohol attacks this group. And then bromide displaces our alcohol via an SN2 reaction. That in turn gives us the alkyl bromide installed with inversion of stereochemistry. And then for the thiophenol, that's our nucleophile, the thiophenolate anion, then attacks our alkyl halide with inversion, and that in turn yields a net retention of stereochemistry over these two steps. Does that example make sense to everyone? Does this make sense to everyone so far? Perfect. So this is a good stopping point for today's lecture.